It's my great pleasure to introduce Ariyan Javanpeykar from Universitat Mainz, who will tell us about Albanese maps and fundamental groups of varieties with many rational points over function fields. Go ahead, Ariyan.
Thank you very much for the introduction, and thank you very much for inviting me and for organizing this. It's a pleasure to speak here. So I'm going to tell you a little bit about fundamental groups of varieties with many rational points over function fields. But before I get to tell you about this, I want to tell you how I got how I got started on thinking about questions related to these objects. And this really goes back to Campana's conjecture. So to explain Campana's conjecture, let me denote X always a smooth projective connected variety over the complex numbers. And I'm going to talk a little bit about special varieties. So Campana's class of special varieties, if you haven't seen this before, then basically you can think of the opposite of being of general type. So it's a class of varieties which is as far away as possible from the class of varieties of general type. And those are exactly the varieties with canonical bundle big. So I think the precise definition would be a little bit too technical to give you. So let me give you an idea of the definition. It's actually not really the definition as Campana gave it. He gave another definition and proved that this is equivalent to what he did. So I'm going to talk about fibrations, which just means surjective morphisms with connected fibers. And I'll say that a fibration is of general type if the base variety, if its canonical bundle perturbed with a little small effective divisor is big, and the dimension of the base is positive. And so this perturbation, this delta F here, this is some effective Q-Cartier divisor encoding the multiple fibers of F. So what I'm not going to tell you exactly how to define this, but basically it's the infimum over all the multiplicities of all the fibers of points of fibers lying over points of codimension 1. But what I would like you to take away from this is the following example, which is that if Y is of general type, so I put it here, and the dimension is positive, then any fibration onto Y is of general type. Okay, so but it could be that you have a fibration of general type and the base itself isn't of general type. Only when you perturb the canonical bundle with this effective delta F, it becomes big. All right. So what does it mean to be special? I put this extra big. X is special if it does not admit a fibration of general type. Okay, so in particular, what that means is that a special variety, it does not dominate any positive dimensional variety of general type. Okay, so basically a special variety cannot dominate a curve of genus at least 2. Cannot dominate hypersurfaces, smooth hypersurfaces of very high degree in projective space. This is what I mean by special varieties are as far away as possible from being of general type. So again, to reiterate, general type fibrations means that the base, the canonical bundle of the base, endowed with this, when you add this additional effective Q-Cartier divisor, is big. Okay, so I'm going to go a little bit fast over this because the definition won't really matter. What matters is the following examples and a conjecture of Campana in characterization of special varieties in an analytic sense. I'll get to this in a second, but now I'm going to first tell you what the one-dimensional special varieties are. Well, which one-dimensional special varieties don't dominate curves of genus at least 2? Well, these are exactly the curves of genus 0 and the curves of genus 1, right? So being special for a curve literally is equivalent to being not of general type. This is no longer true in higher dimension. So this genus 0 business here, in higher dimension, well, okay, what's the analog of a genus 0 curve? A rational variety, unirational variety, or even a rationally connected variety, you could say. And it turns out that if X is rationally connected, then it is special. Okay, so this is kind of the genus 0 case in higher dimensions. And the genus 1 case in higher dimension is, for instance, that if X is an abelian variety, then it is also special. All right. So sometimes you'll see that I haven't completed the notes because I don't want it to go too fast. So rationally connected varieties and abelian varieties are special, but actually genus 1 is more, the analogy would be Kodaira dimension 0. And in fact, if X has Kodaira dimension 0, then X is special. So for instance, K3 surfaces are special, but also Calabi-Yao's and Enrica surfaces and hypercator varieties. Now, I want to reiterate that special does not mean not of general type. For instance, P1 times a curve of genus at least 2, right? This is neither special nor of general type. Special really means it cannot even be mapped to a variety of positive dimension of which is of general type. So what I'm interested in is a conjecture, but I thought I'd leave the opportunity from now and then to answer questions, but then you have to be quick because I want to continue. So the conjecture that I'm interested in is basically the following conjecture of Campana, which says that a variety X, which is smooth and projective, is special if and only if it has a dense entire curve. Okay, so what does that mean? That means that there is a holomorphic map from C into the analytic space associated to X, the complex manifold associated to X in this case, such that the image of this holomorphic map is Zariski-dense in X. Okay, this is the conjecture for special varieties that kind of is the starting point of all this. It's an analytic characterization of what it means to be special, and it's kind of the opposite of a well-known conjecture about varieties of general type. For varieties of general type, the conjecture by Green, Griffiths, and Lang is that if that the variety X is of general type, if and only if X is what's called pseudo-hyperbolic, so this is terminology that was coined by Kobayashi and Lang, but this just means that there is some proper closed subset. So there is some proper closed subset such that every non-constant map from C into X lands inside delta, let's say factors over delta. All right, so let me just point out the similarities, but the kind of the reverse similarities. So X is special, that's opposite to being of general type, right? These things are two opposite. And having a closed subset which contains all the non-constant holomorphic maps from C is kind of opposite to having a holomorphic map whose image is Zariski-dense, right? So by kind of flipping around what it means to be pseudo-hyperbolic, you're led to conjecturing that if you believe that special is the exact opposite of general type, that then there should be a holomorphic map inside every special variety. So today's focus will be about Campana's conjecture. So here's a slide with a lot of colors. I think I might have overdone it here. So the conjecture of Campana is that you're special if and only if you admit some dense entire curve. So this conjecture can be proven if X is one-dimensional, right? So if X is one-dimensional, then we know that you're special if and only if you have genus at most 1. And this is the same thing as admitting a map which is non-constant, in this case dense because it's one-dimensional. So non-constant. And that's because these two curves are uniformized by the open unit disk. And if you're uniformized by the open unit disk, well, then you're hyperbolic. And so you have no entire curves. So this is the same thing as saying there exists a dense entire curve because of the one-dimensionality. Right, so in dimension one, the conjecture of Campana, which says that special and having a dense entire curve should coincide, is true. And for abelian varieties, of course, it's also true. X, in this case, is special and has a dense entire curve. This is because it's uniformized by affine space. Right, so in this case, the conjecture is also true because in this case, you even have a uniformization of the analytic space by affine space. The final result, if you remember, I kind of said, okay, so you have abelian varieties and then you have rationally connected varieties. These are special, so one expects also in this case that we have a dense entire curve, and actually this is a very recent result of Campana and Winkelmann. So if X is rationally connected, then X has a dense entire curve. And this result is motivated by his conjecture that you're special if and only if you have a dense entire curve. So the question I'm interested in is what topological properties do or should special varieties have? And here, the leading conjecture is called the abelianity conjecture, okay, by Campana, which says that the fundamental group of X is virtually abelian if X is special. Okay, so what does virtual abelian mean? This just means that it has a finite index subgroup, which is abelian. So all in all, we expect special varieties, in particular varieties with a dense entire curve, to have a virtually abelian fundamental group. That's the point I'm trying to make in this first part. And of course, if A is an abelian variety, so the analytic space associated to A is a complex torus, then the fundamental group of this A is abelian, right? It's a lattice. And if X is rationally connected, then this is also true because such varieties are simply connected. So we see that, and this is a theorem of Campana and Kolar, Miyaoka, and Mori. We see that in these two cases it's true, but in general it's not known. It's not known whether a special variety has its fundamental group virtually abelian. But there are two beautiful theorems. And these theorems say that if X is, say, special, then every linear quotient of the fundamental group of X is virtually abelian. Okay, so what do I mean by linear quotient? I just mean the image along a representation, a linear representation. So this means if you have a homomorphism from pi1 to GON, then its image is virtually abelian. Okay, so this is a theorem about special varieties. Let me highlight this. This is a theorem about special varieties that says that if you're special, then every linear quotient of the fundamental group is virtually abelian. And Yamanoi, motivated by Campana's conjecture, said, well, if X has a dense entire curve, of course, conjecturally it should be special, if you believe Campana's conjecture. But so that suggests that the same result should be true. And the same result is in fact true. This was proven by Yamanoi in 2010. And in fact, every linear quotient, so it's the same statement with a different assumption, then every linear quotient of pi1 is virtually abelian. Right, so this is, these are the two theorems that kind of form the starting point of this story. And they're really motivated, right? So it's kind of the same conclusion with different assumptions, but the assumptions are conjecturally equivalent. And the work I'm doing with Erwan Rousseau is concerned with the function field analogs of Campana's conjecture on special varieties over number fields. So actually, Campana conjectured a little bit more. He also has some arithmetic conjectures, which say that if you're special, then you basically have a dense set of rational points valued in a well-chosen, some suitable, finely generated subfield. Of course, you have to choose a model, so the precise statement is here written on the whiteboard. But basically, you should think of it this way. If you have a variety, then it's special if and only if it satisfies potential density of rational points. And that's exactly opposite to Lang's conjecture, because Lang's conjecture says something about general type varieties, right? So Lang's conjecture says that if you're of general type, well, that's the same as saying that you have some proper closed subset such that the rational points are finite. And Campana's conjecture, which is opposite to Lang's conjecture, says that if you're special, in this sense, then the rational points at some point are dense for some well-chosen choice of finely generated subfield. Finely generated subfield, by the way, just means finely generated over Q. Now, the arithmetic setting is interesting, but unfortunately I don't have much to say, so I will focus on the function field analogs. But this is not really investigated by Campana, so we decided to make a precise definition, and here's our definition. So we say that something is geometrically special if you find for every dense open subset some point and also some pointed curve. So pointed curve means smooth, projective, connected curve with a point and a sequence of maps, of pointed maps. So there's some sequence of pointed maps which cover the constant family X over C. And you might now wonder what this means, cover C times X. This just means that the union of the graphs is dense in C times X. Okay, so I take the union of all graphs, and then I get a dense subset of C times X. So in words, so let me tell you what this means in words. I'm going to click away. It might be a little bit fast, but basically in words, X is geometrically special if it satisfies some form of pointed potential density. So you might object to, why am I asking for maps that respect base points? Well, this is because without the pointed version, you could just use the constant sections of P1 times X to cover it. But once you add base points, then this won't work, of course. So we're getting rid of this, of the constant sections in some sense, right? So we're looking at sections of C times X, and we're looking at those that pass through a given point and which map a given point to a given point, in fact. And I want those to cover my entire variety. All right, so the conjecture we propose is that this notion of geometrically special, so let me go back to the precise definition, this notion of geometrically special, that basically for a dense set of points X, you can find a pointed curve and a sequence of pointed maps which cover C times X. This notion, which is just a notion defined for a smooth projective variety over the complex numbers, this should capture what it means to be special. So if you want in words, this conjecture is saying X is special if and only if X satisfies a potential density of pointed rational points over some function fields. All right, and of course, if you believe this, then you want to check it first in some easy cases. So in the easy cases that the dimension is 1, then this is true by standard finiteness theorems of de Franquis and Severi, because basically maps between curves, there's only finitely many if the genus of the target is at least 2, finitely many non-constant ones. And if you're an abelian variety, then it's also true that X is so special and geometrically special, right? So this we already knew. And then finally, here we also have that such varieties that are special are also geometrically special. So that's kind of the evidence for this conjecture, but the conjecture predicts that if you have a geometrically special variety, then its fundamental group, every linear quotient of it should be, in fact, virtually abelian. Right, so this is basically the analog of Campana and Yamanoi's theorem. If you take a geometrically special variety, then every linear quotient of pi1 of x is virtually abelian. And I want to tell you a little bit about the proof, because you see the way we prove this is by realizing that if you look at the proof of Campana, and you look at the proof of Yamanoi, then there's properties that are used of special varieties or varieties with a dense entire curve, which are kind of the same. It's almost as if you're kind of running the same proof, but you're just using certain properties that these classes of varieties have in common. So that's basically the idea. So we're going to use that the class of geometrically special varieties and the class of special varieties, we're going to use that kind of in the back of our mind, that they have many common features, right? And then we're going to kind of redo the proof. So I won't get into the details of the proof, but there are these 2 common features I'd like to mention. So for example, if X is geometrically special, or X is special, or X has a dense entire curve, then there's this property about the Albanese map, which is true, which is namely that the Albanese map of such a variety is surjective with connected fibers. So this is a very important step in all the proofs. Meaning that if you look at Campana's proof, then this is used. If you look at Yamanoi's proof, then this is used. And also in our proof, this is part of the line of reasoning to show that every linear quotient of pi1 is virtually abelian. And another ingredient of our proof is Hodge theoretic. And so it goes back to work of Deligne, Griffiths, Schmidt, Kang-Zuo, and also uses the Baker, Brumbach, Zimmermann resolution of the Griffiths conjecture for algebraicity of period maps. And it's the statement that if you have a geometrically special variety, or a special variety, or a variety with a dense entire curve, then every period map, so a priori complex analytic, period map on X is constant. And a period map is an integral, a polarized integral variation of Hodge structures. So these are 2 of the ingredients. I won't tell you much more, but I'll thank you for your attention. I hope you stay healthy.
Thank you for that wonderful talk, Ariyan. Let's thank him either by clapping with the sound on or by typing clap into chat. So there are quite a few questions, and we were actually running a little over schedule, so maybe we have time for just a couple questions. So I think there are two people who have raised their hands. I'm going to allow you to talk, Fumiaki. Do you want to unmute yourself and ask a question? All right, maybe, oh, go ahead. All right, I think maybe Fumiaki's microphone isn't working. If you'd like, do you want to type your question into chat? And in the meantime, I'm going to unmute Bert. And do you want to ask your question, Bert?
Yeah, I was just going to ask, so for example, is it known that like every projective K3 surface has a dense entire curve?
Did you ask about K3 surfaces? Whether
Yeah,
they have...
is it known that everyone has a dense entire curve?
No, that's not known, no. It's known for elliptic K3s, as far as I know. So elliptic K3s, or those with many automorphisms, then it's known that there is a dense entire curve. But as far as I know, it's not known whether, for instance, if you take a general K3, so one with Picard rank 1, whether this has a dense entire curve. It's also not known whether this has a dense set of rational points in some finely generated subfield. And it's also not known, to my knowledge, whether it's geometrically special, so whether it's covered by pointed sections in this sense. Yeah. Does that answer your question, Bert?
Oh, yeah, yeah. Thanks. Yeah, thanks.
Jordan also has asked a couple questions in chat and raised his hand. So maybe, Jordan, I've allowed you to talk. Do you want to unmute yourself and ask your question?
Oh, sure. Although I think maybe people sort of answered it in the chat, but I was just, actually, I think the question about the unipotent stuff, I think was reasonably answered in chat. So I don't think I need to ask it. Can I ask a different question though, that I just came up with?
Yeah.
I was just thinking about as you startled me by unmuting me. I mean, this question about whether something like a K3 is covered by pointed, let's say, so you're asking about whether pointed rational curves cover a K3. My memory is that people often talked about maybe that's different over like a finite field than it is over C. Like I feel like, you know, Yuri Chinkol and Fedor Bogomolov used to talk about stuff like that. Do you have some sense about whether the answers to these questions might truly be different in those two contexts?
In the characteristic P and the characteristic 0 context. Yeah. I don't have a good feeling about it now, but maybe in a couple of minutes. 1 second. So I think in characteristic 0, it seems very reasonable to suspect that you can cover a K3 with pointed elliptic curves. Maybe not with pointed rational curves, but maybe
no,
with pointed,
yeah, I would think not.
Yeah, because
But
but in characteristic P, maybe over large enough fields, yes, but maybe not over FP bar. But this is just a wild guess, and it's not really an educated guess.
All right, I think there are a couple very quick questions in the Q&A that I think might be worth going over. So Michel Graffeo asks if the closure in the definition of geometrically special is Zariski closure, or I guess it's analytic closure?
No, Zariski.
Okay.
Yeah.
And then I guess in part your conjecture might answer Austin's question, but he wants to know if there's an algebraic reformulation of Campana's conjecture, like without using holomorphic maps.
Well, there is a conjecture without using holomorphic maps, probably, but it won't be a reformulation of the conjecture. It will just be another conjecture. So basically, there are, but I don't think you. I mean, no. So I mean, of course, a dense entire curve has to be highly analytic, right? This has to be a very holomorphic map. I don't think you can formulate things algebraically. This is a really transcendental statement. You might have an analogous statement that you could expect by using maps from abelian varieties. So you could maybe hope that there's some sequence of abelian varieties. So this might be the same. So there exists a dense entire curve, and I'm just kind of improvising, but this might be the same as asking that there is a sequence of rational maps from some abelian varieties which cover, in some sense, X. But don't quote me on that. Right? So that would be maybe some algebraic reformulation of this, because AIs here, these abelian varieties, they're uniformized by affine spaces.